upon that information? The answer is you don't. We need much more details. So what I suggest is this, that once we identify those big hotspots, what we do now is that we take that code and we parse it into different segments. So we parse each function, each method inside that big file, and then we run a hotspot analysis on that level. So we look where the different commits hit and sum it up. Let me show you how it looks on gc.cpp. So here's the hotspot analysis on a function level of that huge file. And we see that the number one hotspot is a function called grow brick card tables. It consists of 332 lines of code. That's quite a lot for a single function, isn't it? But still, it's much less than 37,000 lines of code, which was the size of a total file. And it's definitely less than 4 million lines of code, which is the size of a total system. So even more importantly, we're now on a level where we can act upon this information and do a focused refactoring based on data from how we actually work with the code. So we're going to return to the hotspot soon again. But before we do that, I want to answer a question. How do we get to 37,000 lines of C++? Well, let me give you a small book recommendation. This is a book by Diane Vaughan called The Challenger Launch Decision, and it's one of the best books I know on how organizations fail. So Diane Vaughan uses the Challenger accident to frame her theory of normalization of deviance. So how many of you remember the Challenger accident? So like half of you maybe. All right, so let's do a quick recap on Challenger. This is the Space Shuttle Challenger on its final launch. And here's the actual space shuttle. And what you see here, this huge white object, that's a solid rocket booster. And you see that puff of gray smoke here? Not a good thing. It's not supposed to be there. So what actually happened was that those solid rocket boosters, those are huge, huge things, right? So they're delivered in 3 separate segments that are assembled before launch. And it turned out that one of the joints in those solid rocket boosters leaked, and hot rocket gases were able to escape and impact the structure of the Challenger. So once it got into the air, it simply disintegrated. Now, the interesting thing here is that Diane Vaughan writes that back in the 70s, during the early design tests, they found out that those solid rocket booster joints, their actual performance deviated from the predicted performance. Now, what do you do when you find such a thing? If you're NASA, you form a committee. So they did, and they discussed the problem, and they decided to pass it off as an acceptable risk. Years later, as they did their first in-flight tests, again, the measures showed that the actual performance of those solid rocket booster joints deviated from the predicted performance. Again, they discussed the problem and passed it off as an acceptable risk. And they continued to do that over the years, before, on the very eve of the launch, there were some concerns raised by some engineers due to the unusually cold temperatures in Florida at that time. And again, the problem was discussed and passed off as an acceptable risk, and the consequence was a tragic loss of lives. Now, that's what Diane Vaughan calls the normalization of deviance. And that means that each time you accept a risk, the deviations become your new normal. You get a new point of reference. And this is interesting to us because the normalization of deviance is not about spaceships. It's about people. People that build software. And we have plenty of normalization of deviance in software development too. Let's say, for example, that you inherit a file with 5,000 lines of code. If you work with that file long enough, those 5,000 lines will become your new normal. And I mean, besides, what difference does it make with a few extra 100 lines of code, right? So soon you have 6,000 lines of code. Then you have 7,000 lines of code, and so on. So we need to find a way to stop and fight the normalization of deviance. And one really simple technique that I tend to use is something I call complexity trends. Here's how it works. what I do is I take a hotspot and then I pull out each historic revision of that code and I measure the lines of code and the code complexity at each point in time. And I plot them as a trend like this. Because you see, all systems have stories to tell. We just need to learn how to read them. So take this one, for example. We see the code complexity here. In this case, it's cyclomatic complexity. We see that there seems to have been some kind of refactoring back in 2016. So we actually managed to drop both the lines of code and the complexity. But we probably failed to address the very root cause. So pretty soon, the complexity keeps keeping back in again before there's a huge, steep increase in complexity at the beginning of 2017. So the normalization of deviance is one reason that whistleblowers are important. And I have found that complexity trends make great whistleblowers in code. So to sum up this first part, hotspots help us identify the code with the highest interest rate. And the reason they work is because all code isn't equal. Now, I would like us to have a look at software architectures. And as you all know, you cannot really talk about software architecture without mentioning art. So have a look at this art here. How many of you recognize this? None of you. That's very, very good, because this one doesn't exist. This is a liquid crystal light projection done by the artist Gustav Metzger. And the fascinating thing with it is that it changes all the time. Right? So it looks completely different now than it did just 1 hour ago. And the interesting thing is the way it changes. Because the way it changes is that a new form necessitates the destruction of an existing form. And this is just how code is supposed to evolve. And successful code will change, it will evolve, and that's a good thing. The reason I say it's auto-destructive is because in many systems, changes and new features tend to become increasingly more difficult to implement over time. And some systems that just seem to reach some tipping point, and beyond that point, they become virtually impossible to maintain. So, how can we identify that? Well, we do have our hotspots, right? But in a large systems, that information is too low level. We don't want to look at individual files. We want to look at semantically more interesting units. So what I suggest is this. Instead of focusing on individual files, we work with groups of files. So we may take a whole group of files and organize them into a logical component. Perhaps our architecture even follows a folder structure, so we can map whole directories to logical components. And what we do now is that we run, again, exactly the same analysis, but now on the level of logical components. And once we do that, we can start to ask a lot of interesting questions around architecture. I would like to show you an example on a bunch of different architectural styles. And I would like to start with a service-oriented architecture. Now, a hotspot analysis on an architectural level helps us answer one of the big questions we have around microservices. This is a question where many flame wars have been fought. Friendships have been ended. And that question is, how big is a microservice supposed to be? 100 lines of code? 1,000? 2,000? As you all know, it's a little bit of pointless to reason about that in terms of lines of code. Because what we want to focus on instead is behavior. We want each service to implement a single business capability. The key is cohesion. So let's see how we can get there. Now, if I want to do hotspot analysis on a service-oriented architecture, what I do is I group all files, all contributions to those files for each service here and calculate hotspots on that level. So here's an example from a real-world system. In this case, you see that the number one hotspot on the architectural level is something called a recommendations service that now consists of approximately 5,000 lines of code. Now, just as we can do hotspots there, we can aggregate the complexity trend information and project a complexity trend for that particular service. And then we see that there was some initial development. It rose pretty fast to a certain level of both complexity and lines of code, and then it seems to have stabilized at a very high level with very rapid changes. Now, you use this information to ask questions. And that a question in this case could be, does this service with 5,000 lines of code and rapid changes really represent a single business capability? Or is it perhaps a service that would be better off when split into 2 or maybe even 3 different parts? Hotspots help you ask the right questions. But we can do even more with this kind of data. And I would like to show you how by introducing a different kind of analysis. This is an analysis called temporal coupling. And temporal coupling is a bit different from the way we typically talk about coupling, because this kind of information, or change coupling, which is actually a better name, is something that you cannot see in the code alone. So here's how it works. Let's say we have this simple system with just 3 different subsystems. The first time we do a change, we modify the fuel injector and the diagnostics module together. The second time we do a change, we modify something else. And the third time, we're back to modifying the fuel injector and diagnostics module again. Now, if this is a trend that continues, there has to be some kind of relationship between the fuel injector and diagnostics module, because they keep changing together all the time, right? So this is something we can use to evaluate our architectures. And I want to show you how you use temporal coupling to do that. And I want to start with the layered architectures, because layers is still a very, very popular pattern. So what you see here is the canonical 3 building blocks of a model view controller. And when I come to different clients and analyze their code bases, I always start by asking them, what kind of architectural style do you have? And I often get the answer that, yeah, we use a model view controller, we have a model view presenter, or model view model, or some of those variations, right? And then you look at the code, and that's not what it looks like at all. Because we all know that this is not enough. We need to have a services layer too, right, for all that behavior. And of course, we must have a repository layer. And the reason we must have a repository layer is, I actually have absolutely no idea. I never came up with a good reason for that, so let's just call it the best practice and go with it, right? And then, of course, below that, we don't want to access our SQL directly, so we use an object relational mapper, and then maybe we have some SQL. And in reality, we may have many, many more layers, things like view helpers and stuff like that, right? All right, so if we want to look at change coupling on this level, we consider each layer here as a logical component. We aggregate all contributions to that layer, and then we look at the change patterns. What do you think the change patterns look like in a layered architecture? Something like this. In fact, I have found that in layered architectures, 30 to 70% of all commits tend to ripple through the whole stack. And this is really, really interesting, because this has a number of implications for us. So what this basically means is that few changes are local, right? And it's interesting when you go back and look at the motivation for different layers, because that motivation is often a separation of concerns. However, it's a separation of technical concerns. These are all technical building blocks, but the work we do, the features we work on, they are problem-oriented, they are feature-oriented, they're oriented towards the end user's view. So there is some kind of imbalance between what the architecture expresses and the work we actually do. And I've found that layered architectures, they tend to work pretty well for small teams. The problems I've seen is when those teams start to grow, where you get more people working on the architecture. And the reason for that is because now you have everyone basically working in all parts of the code all the time, which not only introduces the risk of coordination issues, it also introduces the risk of conflicting features. So I think that this is one of the challenges that are behind the reason of the recent popularity of microservices. So this is what microservices always look like in PowerPoint. In reality, we know that they are much more complex, right? We may have shared building blocks, we may have service templates, client APIs, we may have cross-cutting concerns like monitoring, diagnostics, and so on. So the thing, and all that extra complexity, all that additional complexity put us at risk for the cardinal sin in microservice architectures. And that cardinal sin is strong coupling, right? The moment we start to couple different services to each other, we lose most of the benefits of microservices and are left with an excess mess of complexity. So, if we have an important architectural principle like loose coupling, why don't we supervise it? So what I recommend is that, again, introduce logical building blocks for each service, aggregate the contributions, and look for temporal coupling patterns that crosses service boundaries like this. If you do that right, you can use temporal coupling as an early warning sign that lets you catch potential problems and react before they become big issues. In fact, it may even help you avoid what I call the microservices shotgun surgery pattern. So the microservices shotgun surgery pattern, that's basically the case where you want to tweak a single business capability and you end up modifying 5 different services. And I've seen several reasons why that happens. One of the most common reasons is that the different services that tend to share code that itself isn't stable from an evolutionary point of view. Another very common case is that services are sometimes leaky abstractions, so that other services tend to depend upon internals, and now they have to co-evolve. Finally, I've seen that this is more likely to happen when the same team is responsible for multiple related services. All right. What kind of tools do I use to do change coupling analysis? Well, there are a number of different options. When I started out with these analyses several years ago and wrote my book, Your Code is a Crime Scene, I didn't find a tool capable of doing all the combinations of analysis I wanted to do. So I implemented my own tool suite. It's available on GitHub, completely free to use. I still maintain it. So that may be a good starting point if you want to play around with these analyses. What I work on right now is something called CodeScene, which is basically my attempt to automate all of this stuff. And there are also some and there's also a free plan on CodeScene. So if you do some open source, check it out, give it a try. There are also some interesting alternatives in the academic world. One of my personal favorites has to be the evolution radar, which is particularly strong on temporal coupling. And then, if you want to build your own tools, I recommend that you have a look at the Moose platform. So the Moose platform is a framework for building code analyzers. And it's one of the best excuses you will ever find to learn to program in Smalltalk. It's a fantastic language, I love it. So let's sum this up. We have seen that hotspots scale all the way from functions to files to architectures. And we have seen how we can use temporal coupling to evaluate our architecture. Now I want to spend the final 10 minutes on exploring the social side of our code. So before I do that, let me ask you, how many of you develop software as part of a team? That's like 95% of you. Cool. Yeah, we have to do that, right? Because we take on larger and larger problems. Our code bases grow ever larger all the time, right? So we cannot handle that alone. We need to get together. What's interesting, though, and what we almost never talk about, is that teamwork always comes with a cost. And that cost is something that social psychologists call process loss. And process loss is a concept that social psychologists have borrowed from the field of mechanics. And the idea is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. So let me illustrate that for you. Let's say we have a bunch of individuals here. Together, they have a potential productivity. But that's never, ever what we get out. The real productivity is always going to be a bit smaller. and part of the potential is simply lost. Now, the kind of process loss you get depends on the task you do. But I would say in a complex world like software with a lot of interdependence between the tasks, most of our process loss is probably due to communication and coordination overhead. Another reason for process loss is what social psychologists call diffusion of responsibility. Now, the diffusion of responsibility is something that you can witness if you're unfortunate enough to see an accident or an emergency, because what happens in that case is that the more witnesses, the more bystanders, the less likely that an individual will offer help. This is actually quite scary. And there are several reasons for that, but one of the major reasons is, of course, that the more people that are present, the less personal responsibility do we feel. We just assume that, oh well, someone else will help instead. And it's exactly the same in software. We must feel that our individual contributions make a difference. And I'm pretty sure that good code is code where you have a sense of personal responsibility for everyone involved. I don't really think there's a way around that. So, if we have a thing like diffusion of responsibility, how can we measure that? Well, remember, we're in version control wonderland. So we know exactly which developer that worked with which parts of the code. So let's aggregate individuals into teams. Here's one way of doing that. So this is an analysis that took out of a research paper I reference here. And this is exactly the same style as we use for the hotspots, only now the color signals a different meaning. The color here signals the amount of potential coordination overhead between different teams. So the more different teams work in a part of the code, the more red that part of the code. And this is not just about the number of teams, but also how diffused their contributions are. So using this data, we can identify those areas where we have potential coordination bottlenecks. And once you find them, the bad news are that there's no easy fix. There are two things that I've seen work in practice. The first is to take a technical look at that, because one of the main reasons that code attracts many different teams is because it has too many responsibilities. It's low on cohesion. So taking a technical look and splitting that shared code into cohesive modules will not only give you a better design, but it's also something that will help you limit the amount of coordination. Another thing that I've seen is that sometimes in large organizations, you may have to introduce a new team to take on a shared responsibility. And that's quite often the case when you have things like frameworks for integration tests that need to be up to date with your product you're running and testing. Because those tends to be a collaborative effort, and the end result is that in most of the analysis I do, the worst hotspots are always in the test code. So you may have to introduce a team to take over that responsibility. But we can do even more. With this kind of data, we can start to evaluate things like Conway's Law. And I want to show you a simple example here. Now, this time, you see that we have a bunch of different teams here, and each team is assigned a color. And the team that have worked the most with each part of the code, they get the color of that part of the system. Now, this is a package by feature architecture. And from the perspective of Conway's Law and the diffusion of responsibility, this looks marvelous, doesn't it? Each team have their own part where they can work in complete isolation with a minimum of coordination overhead. However, I have to make a small confession here. All data that you have seen so far are from real-world systems, except this one. I had to make it up because I haven't found an organization that's that well aligned with the code. And I'm not even sure if it's a good way to go there. I think once you get there, you get into a bunch of other problems. But that's something I can talk about afterwards. Now, I want to show you something much more common, a much more common pattern. And this is what you tend to find in many large organizations. Have a look at this. This is a story about a company that wanted to introduce feature teams. And the way they did it was that they took the organization, and split the developers into 12 separate feature teams. And at the start of each sprint, each team was assigned a number of tasks, and then they get loose on the code base. And this is what their contribution patterns look like on a team level after a single month. Do you see any patterns here? It's really, really hard to spot some patterns, right? There may be one or two parts that are almost in the hand of a single team, but not really. In fact, I would like to say that this is collective chaos. This is a complete coordination disaster. And the reason I say that is because what happens here is that you have 12 different teams working the same parts of the code all the time for different reasons, because they all work on different tasks. And this is going to be expensive. In fact, I will also say that one of the things you lose here is the opportunity to detect synergies between different features. That is an opportunity to simplify not only the problem domain, but also the solution domain. So please, align your architecture and your organization. Your code is going to thank you for it. So I've come to the end of this presentation, and I hope you enjoy this journey through the fascinating field of evolving code. Ultimately, it's all about writing better software. Software that's able to evolve with the pressure of new features, novel usages, and changed circumstances. And writing code of that quality is never going to be easy. So I'm pretty sure that we need all kind of support that we can get. And I hope that this presentation has inspired you to investigate the field in more depth. And if you want to get started, I put together a number of references. I have 2 books about this, Your Code as a Crime Scene and Software Design X-Rays. Both of them, by the way, are on sales right now, Thanksgiving sale, with the coupon Turkey 2017. You can check my Twitter if you forget that. I also blog a lot about this at mpere.com, so check out my blog if you want to read some more case studies. And now, before I take some questions, I would like to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thanks. We don't have a microphone, do we? I think I have a few minutes for questions.
This kind of study, is it something that is a job for a person to do it continuously, or it's something like you review this, let's say, every year or every month, or how often do you do this kind of study?
Yeah. So how often do I do an analysis like that? It depends on a lot what you're after, what kind of questions you have. So in some cases, what you have is a huge legacy code base, and you need to improve. You need to get more productive. Then you do an in-depth analysis, and you prioritize all that stuff. And of course, when I do that, I also use different kind of tools. But once you've gotten up to a certain level, you can actually start to use the same techniques to get early warnings. So, for example, I've been building these techniques into things like continuous integration pipelines, which is pretty interesting, because not only can you get an early warning for things like complexity trends, already on our feature branch, right? So if you merge this code, you're actually going to get the complexity trend warning. You can also get quite fascinating warnings. My favorite is if you look at, remember temporal coupling, where different parts, files, and functions change together. So what I do is I look for that in our continuous integration pipeline, because if you do an analysis, you know that these 2 files, they're going to change together all the time. And if you suddenly see a commit where one of them isn't changed together with the other one, that may be a potential bug, right? So that makes it kind of like a, you know, the minority report of software, right? It can tell you that, hey, you did a change to this file. Usually when we do that, you also tend to change the part over here. Did you forget that? So I think there's a lot of promise here. And it's an area I've really just started to explore. Do we have time for, I think one more question?
Hello? Yeah. Okay. You know about Git, right? And you know that a lot of people that use Git do tend to rewrite their history, do rebases, erase merges, do cherry picking, do a number of, I personally call them craziness, but okay. Based on what you have described on your techniques, I would say that they're rather sensitive in if you are using this kind of techniques, right?
Yeah, sure. So it's something I come across in real life, of course. My experience is over the past years, not only has the share of Git users increased quite dramatically, people are also starting to use better workflows. So a lot of that craziness is something that I think we have more in the past than in the present days. But it's a very real problem. It's something that happens if you, for example, use squash commits, where you take, we have this bunch of commits, let's squeeze them together and pretend they're a single commit. So that's something that has an impact in particular on the social metrics. The hotspots and the technical analysis, they tend to work pretty well, even in those situations. But the social metrics are very sensitive to that once you blur their true offer information. So that's something like all kind of data analysis. That's what you always start with, to explore your data and ensure that you have the proper data you need to do what you want. Hope that answered your comment. So if you want, grab me afterwards. I have some beautiful Codes of Crimes and stickers. You want one? Thanks a lot and enjoy the rest of the conference.